Okay, are we ready? Okay. It's my great pleasure to introduce our colloquium speaker today, Professor Kerry Vahala, who is a Jenkins professor and professor of applied physics at the California Institute of Technology, so a very good institution. So Professor Vahala received his bachelor, master, and also PhD degrees at Caltech. So his research group has pioneered a class of optical resonators that holds the records or the highest Q on a chip. So Professor Vahala work actually has a lot of influence on my own research. When I was an undergrad student, one day I figured out a way to make this small tiny sphere. At that time I had a 100-watt CO2 laser, so it's a powerful laser. So one day I focused the laser beam on a piece of glass, and somehow I formed a microsphere, like out of it. And then I made a bunch of them, because they look beautiful. And I took it to my advisor, and I asked, what can we do with it? Right? So he told me, we can use them as lenses to focus light, right? So when I look at them, I say, there might be other applications because they are so beautiful, right? So, and sure enough, as soon as I got on the internet, I found Professor Vahala work, and basically that got me. So I started to work on this resonator, and we've done only a few small steps, but Professor Vahala group has done tremendous work here. So his group demonstrated, I think, the first Raman laser on the microsphere, right? Mm-hmm. So that was my favorite, I think, paper. And then he's demonstrated the first parametric oscillation on the microsphere as well. And this is a hot topic now because that's the basis for micro-optical frequency comb or microcomb, right? So DARPA that put out a proposal, solicitation a few weeks ago for that. And then, things that go on, a lot of interesting thing. Another important theme is basically the connection between mechanics and optics, right, to the radiation pressure on these platforms. So very interesting stuff that he's going to tell us about. So Professor Vahala received the IEEE Sign-Off Award for his research on quantum well laser dynamics as well in the early days, I guess, a long time ago. He has also received an Alexander von Humboldt Award for his work on ultra-high Q microcavities, and he's a fellow of the IEEE and the Optical Society of America. So it is my great pleasure to introduce Professor Vahala, and he's going to talk to us about confining light on a chip. The science of optical microresonators. Thank you for coming.
Yeah, thank you very much, Con. Okay, yeah, it's my real pleasure to be here today, and nothing makes me happier than to have a chance to talk about high Q resonators. Okay, it's just a very, very fun subject, and I hope I can sort of pass on a little bit of my enthusiasm, and have enjoyed my visit today, and look forward to continuing the visit after my talk. So so basically, yeah, as Con said, I'm going to tell you a little bit about the background on this subject, and I mean, it's interesting. Everybody has their own story about how they came to find themselves in a particular research subject, and so I'm going to begin by giving you just kind of a little bit of a tutorial on high Q resonators. And as part of that story, I guess it'll kind of explain how I found myself in this subject, because there were some other very important pieces of work that preceded some of the work that we've done over the last 15 years. And so I'll begin by doing that. And then I want to spend a few charts describing what is one of the fun things to do, okay, with high Q resonators, and that's to study nonlinear optics, okay. But the nice thing about a high Q resonator is that you can perform nonlinear optical experiments with very, very low powers, okay. And in many cases, you don't need pulsed operation. You simply can apply a very low power continuous wave beam and see all kinds of wonderful nonlinear phenomena. And I want to tell you, a little bit about why that happens and some of the interesting easy things you can do, okay, once you've managed to make a high Q system. And then in looking at what I was going to tell you about in terms of our recent work, okay, today, I had to make some choices. And one subject I debated, and I actually had mentioned it in the abstract, was cavity optomechanics, which is this last subject that Kun mentioned, which is the coupling of radiation pressure with mechanics, and that has become a whole kind of subject with probably around 20 or 25 groups, okay, around the world working in it. And I've actually decided to leave that out of the talk today so I could tell you about some more recent work we're doing, which has to do with microwave generation, and also just a little bit of work on frequency microcombs, and why there's so much interest in frequency microcombs now in terms of some interesting applications. So I'm not going to be talking about about cavity optomechanics. I just want to make that clear up front. Okay, so let's begin, okay, with just some background. So you can go in the literature, and optical microcavities have, the idea has been around a very long time. And so I'm going to make a distinction between a kind of a resonator or microresonator that would have a Q of maybe 10,000 or 100,000, and a Q factor, okay, that would be in this regime that many people refer to as ultra high Q. And I think there is some work that you could point to, okay, in the mid-'80s that sort of launched this whole field. And that work actually was done at Yale and Naval Research Labs, and it was Richard Chang, who is now emeritus, and Tony Campillo. And what they were doing is actually some of the earliest nonlinear optical experiments in high Q microdroplets. Okay, so they would create aerosols of various substances. And what they found is that these little droplets, because of the surface tension smoothing of the surface, would support very high Q optical modes, and you could see the evidence of these modes when light was scattered, okay, from the droplets, and you could see Raman, you could see other types of interesting nonlinear optical physics, okay, that was going on inside these liquids. So in my mind, this is kind of maybe the beginning of this subject. There's another group that really played a pivotal role, and they continue to do so even today. And this is a group out of Moscow State University, and led by Vladimir Berginsky. And then a couple of his students have gone on and actually are now leaders in the subject, Michael Gordetsky, Vladimir Olchenko. And what they did is they kind of adapted this idea of a liquid droplet, okay, that had this wonderful surface tension smoothing to reduce the scattering losses. And they made a solid-state version of it, okay, which is what we just heard about. Okay, if you take a filament of glass, heat it with a CO2 laser, you'll get a little ball, okay, a little tiny sphere, okay, at the end. And if one can find a way of coupling light, okay, into the sphere, and there's a couple different techniques for doing that. One of them you can see out of focus here. There's a little tapered fiber coupler in the back that's allowing light to couple in. Then it's possible to actually observe very, very high Q resonances. And so their work in paper in 1989, okay, actually was the first to kind of demonstrate this idea of a silica microsphere. And at that time, the Q was somewhat modest, okay, by present-day standards. It was around 1 million, okay, but it was enough that it piqued the curiosity of a number of other groups. This is, by the way, a sphere we made at Caltech about 14 years ago, and we doped it with erbium, and you're seeing excited state absorption and emission, okay, from the erbium. And I like to show that picture because it makes very clear that the modes, okay, even in a sphere, okay, that we excite are these little ring orbits. Okay, so you should be thinking in terms of little ring orbits, okay, and the dimensions of these structures can be anywhere from tens of microns, okay, to hundreds of microns in size. All right, so now just kind of continuing a little bit of the history here. If you look into the 90s, there were a couple of groups that had seen this earlier work in the Soviet Union at Moscow State University, and Serge Haroche, okay, in Paris, Jeff Kimball's group, okay, at Caltech. They were interested in cavity QED, strong coupling physics, and saw these spheres as a potential way to do strong coupling, okay, with a very, very tiny cavity. Okay, so the ingredients were all there. They made a lot of sense. High Q, very small mode volumes. And so those groups, okay, a couple of these groups for this reason, primarily cavity QED, started to look at these spheres, these little silica spheres. And by the mid-'90s, okay, the Qs had been moved up, okay, further, just by playing some games with the processing, attention to cleanliness, you are now seeing 10 billion, Q factors. And this was really about the time that I was at a meeting in '95, and I saw some of these results, and it just seemed, too interesting, not to, kind of get involved with it. And so, and I've been really hooked on this subject, ever since. All right, so we started our own little effort on spheres and tapered couplers and nonlinear optics and spheres through the late '90s, and by around 2000, 2002, became interested in this idea of trying to transfer these ideas onto a silicon chip. And there were some students at the time, that were looking at making small disks of silica using lithography and wet etching and dry etching. And a very simple idea that turned out to work very well was to adapt this idea of melting the glass, and in this case using a CO2 laser, but now melting the glass of a disk, to form what we call a microtoroid, so a little ring, of glass that has this smooth surface because the silica has gone through the liquid state. The silica itself has a very low material loss, and so these structures, provided a way of putting onto a chip, a very, very high Q. And so at the time, just in terms of high Q on a chip, they gave a very large boost, to the Q factor. Q's jumped by about 10,000-fold, with the introduction of these structures. And they're still used, by many groups. They're so easy to make, and so many kind of interesting things to do with them that many groups are fabricating these and testing them, in various ways. Now there's another structure that's come along, and again, just kind of giving you a quick historical survey of what's, kind of happened in the high Q arena. And this is one that we do not work on in my group, but we have colleagues at the Jet Propulsion Laboratory in Pasadena and also at OE Waves, a startup company, and that actually were involved in the invention of this structure. And in fact, if you look at some of the names, you'll see Vladimir Ilchenko here. So this is the same Ilchenko that was on this original silica microsphere paper, and he's kind of moved on and now lives in Pasadena, but was involved in developing this crystalline resonator technique. And this is a combination of, again, good material physics, calcium fluoride, magnesium fluoride, materials that were looked at for stepper lithography, deep UV lithography, and so the Corning and a few other companies perfected, this material as a good low-loss medium. And then our friends at JPL, developed this technique to actually mill out the surface and polish the surface so that one could form a whispering gallery. And in this case, the amazing thing is that these whispering gallery modes and these kind of micro-machine structures have the record for Q, of a small structure. It's 100 billion. And if you're interested in knowing how high that Q is, it's interesting if you make a comparison to a waveguide loss, it turns out that the waveguide loss of those structures is comparable to silica optical fiber. So it's a really quite miraculous thing that you can actually confine light to such small sizes with losses that are comparable to what has been worked out over many decades in telecom fiber. So this is another one, and now if you come to the present day, there's actually an exhaustive list. In fact, this is not complete. There are other structures around. If you attend Clio or other conferences on high Q resonators, you'll see that there's various interesting styles of devices that are being studied for various reasons. But this is kind of a list of structures that are one way to one reason I put this up here is that these structures are either involved in cavity optomechanics or they're involved in frequency combs. So this is you can find all of these groups are either involved in one of those two subjects. The structure that I'm going to spend a great deal of time talking to you about today is this one. This is a new structure that we've developed just a few years ago, and it has some interesting advantages over the toroid. Its Q is a little higher, you can see, but it also no longer relies upon this reflow trick. And so that's given us some ability to actually sculpt the shape and actually control the size, and this is turning out to be very important in a couple of applications. All right, so that's just a little bit of history. Now I want to spend some time telling you why, again, it's fun, to actually play with these devices in the lab. And this has to do with, again, two things: high Q, small volume. That's the two secret ingredients. And just to kind of real, basic physics here. I guess sometimes I have visitors to our lab, give them a lab tour. If they know nothing about optics, okay, I always say a microresonator is the equivalent of a tuning fork for light. Okay, and if you think about it, that's not a bad way to describe it. Okay, it turns out that Q and even V, okay, are important in both of those cases. And just as a quick reminder, okay, the Q is important, okay, not only for energy storage, which is what I'm going to talk about in just a moment, but it also tells us the line width. Okay, so if we're scanning across, if this is a waveguide, this might be a toroid or a microsphere or some other resonator, but the light is orbiting like this. The round trip condition gives us the location of the resonances. All right, so you see the series of resonances that would appear in the structure. The line width is determined by the Q. And so just for example, a 100 million Q, which is a fairly typical number for a microtoroid, gives you, if you're pumping or testing at 1.55 microns in the telecom band, that's a 2 megahertz, okay, line width. All right, so why is Q and V? Okay, why are they together so important? All right, so again, suppose that we have a microsphere, okay, like what's shown up here, and there's a waveguide, and we've excited this mode. Q is proportional. It's a dimensionless way of characterizing the storage time. It's the ring down time, okay, of energy in the cavity, okay, measured in cycles, okay, of the light. And so if I manage to couple power, okay, into one of these modes, a steady amount of power, okay, that power will be integrated over a time period, tau, that's proportional to Q. So essentially, Q tells you how you're scaling up coupled power into stored energy. Higher Q, higher stored energy. At the same time, if that Q can be created in a structure, in a whispering gallery mode that is itself very small, okay, has a small mode volume, then what one has succeeded to do is to take that energy, that large stored energy, and concentrated it into a very small volume. And so that means that the circulating intensity, okay, inside the volume can be very high. And so basically the circulating intensity will scale like the input power times Q over V. And if you run a back of the envelope calculation, you realize that the numbers are big. A mode volume of about 500 cubic centimeters is typical for a sphere that has a diameter of about 50 microns. So this would be the number that you would associate with that little ring orbit. If we had a Q of 10 to the 8, we simply can plug in the numbers, and what you find is that a milliwatt of power, which is an easy number to come by these days because you can pick up a Thor Labs catalog or a Newport catalog, and you can find laser sources that'll be in the tens of milliwatts. Okay, so it's a relatively convenient number. The circulating intensity in such a mode will go above a gigawatt per square centimeter very quickly. And that's a high enough number that it immediately puts us in the range where it's possible to access, okay, all of the interesting nonlinearities, okay, of silica in our case, or it could be silicon nitride, or it might be calcium fluoride or mag fluoride, or even new materials that are coming online like diamond, okay, for example, if the Qs can be high enough. All right, so this is really this is the very simple physics of why Q and V, okay, are so interesting and important. All right, and just to kind of some quick experiments, okay, that we did, now many years ago to illustrate again some of the fun stuff that can go on. This was actually a measurement of Raman oscillation, okay, in a silica microsphere like this. So here's the pump, here is the Raman mode, okay, that's beginning to oscillate, and here is the LL curve. Essentially, here's the threshold knee, okay, for the Raman peak. And it's turning on at about 100 microwatts, okay, and so there's a lot of nonlinear physics, okay, a lot of nonlinearity accessible, okay, even, okay, at relatively low coupled pump powers. And the threshold itself, and this is kind of an interesting fact, general scaling rule about threshold in any nonlinear oscillator that relies upon high Q, threshold will always scale like inverse Q squared, okay? And the reason for that is very simple. One factor of Q comes from this energy buildup effect. Okay, so the resonance effect allows you to concentrate, okay, more energy with a higher Q. Okay, but the other Q comes from the fact that actually this is an oscillator. It's a laser oscillator, and a laser oscillator has a threshold, and there's a gain, and the gain needs to overcome that threshold, and the threshold will be lower in a higher Q structure because the losses are lower for the mode. So this compounding of Qs actually means that if we make a tenfold improvement in Q, okay, the threshold of the nonlinear oscillator will drop by 100. All right, and so this is again why high Q is important in these little laser oscillators. And this is showing that it's possible to cascade these devices. So here's the first Raman peak, here's the first Stokes, the second Stokes, and they can be cascaded out, okay, beyond 2 microns. This is another effect that is actually, this happened because there was a postdoc working a number of years ago who, and again, this is, one of the fun things to do with a high Q system. If you were in a garage and you could have a high Q, resonator, and you were playing around with it, and you were thinking, what should I do? Well, the first thing that would cross my mind, okay, if I started to think about the physics, is I would want to put as much power into it as possible, see if I could melt it or do something, weird with it, right? Okay, well, that was the inspiration behind this experiment. And so the person started to turn up the power. Eventually, you see visible light, okay, coming out. And you realize actually that the visible light was there all along. Okay, simply if you turn out the lights, you can see it at much lower powers. And what happens is that there's kind of an accidental phase matching that goes on, okay, from the telecom, okay, out to the visible. And in this case, we're getting essentially this third-order nonlinearity creating blue light. And as you scan across, okay, the telecom band, you'll see all of the colors, okay, of the spectrum. So here's red. And if you pump, okay, in opposite directions, 2 different modes. In this case, we're making some green and yellow. So again, kind of interesting, fun things to do, okay, with these devices. All right. So now what I want to do, okay, I've given a little bit of history and some examples, and hopefully convince you that Q and V are important. And now I'm going to kind of come into the present and tell you about what it is that we are working on. Okay, now what we find kind of fun to work on these days, and also try to give you an idea of why we're working on these areas in terms of maybe some practical applications. And so I'm first going to spend just a little bit of time telling you about this new resonator structure. And again, we are no longer making toroids. Okay, we're doing that for about 10 years, and finally decommissioned our system, okay, about 3 years ago. And everything we do now is actually with this new technique. It's simply become much easier and a more powerful technique to make these resonators. So I'll tell you about that. And then I've picked a number of subjects here. I'm going to squeeze in, if there is time, I have to check the clock, but I'm going to squeeze in just an extra bullet in there, okay, on frequency combs, okay, if I have the time. But I'm going to begin, okay, with microwave synthesis using SPS lasers. This is a very new technique that we are working on right now that is related to frequency combs, but it's using a comb technique, okay, to implement what's called optical frequency division to further improve the stability of a microwave signal. And I'll talk about that. And then these 2 last subjects here have to do with some things that are possible now. They give you an illustration of some of the extra structures that can be microfabricated, okay, now that reflow is no longer necessary, melting, okay, of the waveguide is no longer necessary to drive up Q. Okay. All right, so I want to go back to the toroid for a minute, okay, and explain how this new structure came into being. So this is a little video that shows the last step in a toroid fabrication. And so you're looking at essentially going from here to here. Right, so here we have these little silica discs that have been fabricated through microlithography, wet etching, dry etching. They actually make relatively nice whispering gallery mode resonators. And then this final step, okay, is to zap, okay, literally the little resonators with a CO2 laser. And you'll see the brown area here, which is the silica, okay, melt and collapse, okay, into this little toroidal shape. And so, as I said, this is very easy to do in the lab, and you can just bang out a large number of these structures on a chip. Okay, so the great thing about this is that you can make a large number of these structures, okay, quickly. They're high Q, okay, and there's relatively negligible impact on the silicon, okay, from using the CO2 process. All right, but what has bothered us for many years, okay, and why we are now in this other resonator, is that you can see that the boundary retreats in the process. Okay, so you have this collapsing of the boundary. The size changes. That means that you cannot control the size very precisely. It's also very difficult to make the structures larger. Okay, making large structures has actually become very important in frequency combs, frequency microcombs. And there are some other problems as well. We can't actually integrate, okay, a waveguide. We've always been using taper coupling, and now we have the ability finally to move towards actual integration of high-Q structures with waveguides. And so the new technique, there was really nothing miraculous about it, just a lot of kind of work in terms of perfecting recipes. But this is the complete process flow for making a toroid. There's thermal oxidation, there's lithography and wet etch, there's a dry etch, and then there's this melting process. But what we've been able to do is actually to perfect and clean up this wet etch, so that now this wet etch not only defines the resonator, but also polishes it. Okay, so we have a very, very fine polishing etch, and that polishing etch, okay, gives us the size control that we need without sacrificing, okay, the Q. And I reported on this just a few years ago now, but we call these wedge resonators. They're still pretty much, all of the nice features that were there with toroids are there, but now essentially the size is very, very precisely controlled, and I'll show you how well we can control it in just a moment. But the Qs are high, okay? We haven't gone above 1 billion, okay, but I think that's possible. It's just a matter of spending the kind of effort to figure out the last little bits of what's causing some residual roughness. But the numbers are very high. They're close to 1 billion. All right. Okay, so now with that, I'm going to run through a whole series of different applications that we're working on. And kind of one of the common themes here for today, at least in this set of applications, is making very, very stable microwaves. Okay, and it's not a surprising application. If you have a high-Q optical system, there has been this subject of microwave photonics that has existed from a couple of decades, which is the idea that you take laser sources, you directly detect the laser sources. If the relative stability of the laser sources is high enough, a current is generated. That current frequency, the frequency of the current, okay, can be tuned by tuning the lasers. And this has stimulated a lot of research over the last couple of decades. And so the first part of what I'm going to tell you about is just kind of a way to do that, okay, that kind of basic process, but using stimulated Brillouin scattering. So I'm going to tell you first about some how you can use these wedge resonators to make some very, very efficient, high coherence Brillouin lasers. I'm then going to move on to tell you about something very new, which is this idea of electro-optical frequency division, which allows us to tap in to some extra stability, okay, that is there, it's available, and I'm talking about frequency stability for generating microwaves, okay, using this principle of optical frequency division, but in kind of a different implementation. And then I'll move on and I'll talk a little bit about frequency combs, okay, and some of the work we're doing in that area before concluding. Okay, so Brillouin lasers. Okay, so we have all of these different interesting nonlinearities. Okay, there's Raman. Okay, there are parametric oscillators, which are the foundation of frequency combs. There's essentially optomechanical, okay, interactions. Brillouin is one that has been around for a very long time. Okay, it's well known in fiber optics because it's a problem in fiber optic transmission, and so there are techniques that are used to combat, okay, the Brillouin nonlinearity. And the Brillouin nonlinearity is basically a light wave, okay, that is interacting, okay, with acoustical phonons. And if the intensity of the wave is high enough, this interaction can cause coupling, okay, into another light wave, okay, called the Stokes wave, okay, by way of this phonon, okay, that's emitted. And this process is a problem in fiber optics, but you can also look at it as an interesting way to fabricate or to make a laser. And there's been a lot of groups that have published papers in fiber lasers, okay, over the last decades, okay, showing that you can make very nice, high coherent laser sources using the Brillouin process, okay, in an optical fiber. Surprisingly, this hasn't been possible in microcavities, okay, until quite recently. Okay, this was work out of the University of Michigan by Tal Carmen's group, and this is again our colleagues over at OE Waves and JPL, Lut Malecki, and Andrei Matsko and Ivan Grudnin, okay, doing this in a calcium fluoride resonator. And what they did is to show that you could see the same thing if you worked very carefully, okay, with a microresonator. Now, what's the problem in doing it in a fiber versus or in a microresonator versus a fiber? The problem, okay, as many of you may know, okay, is that the Brillouin process, okay, these acoustical phonons are relatively long-lived, and so this process I described of one wave was called a pump wave, okay, scattering and amplifying, okay, the Stokes wave through interaction with an acoustic phonon, it has a phase matching condition. Okay, and that phase matching condition, okay, has a relatively narrow line width to it. Okay, so if we're looking at, for example, phase matching a Stokes wave, okay, in an optical fiber that will scatter, okay, back into, or a pump wave into a Stokes wave that's scattering in the opposite direction, okay, there will be a frequency shift, okay, that is actually the frequency of the acoustical phonon, okay, in this case about 10 gigahertz, really closer to 11 gigahertz, okay, but the line width, okay, of the process, okay, demands that this has to be matched, okay, to within about 50 megahertz, all right. Now that's not a problem in an optical fiber, okay, and it's not a problem in an optical fiber ring, okay. There's a high enough density of modes, okay, that you can always find, okay, a match. But in a microcavity where the free spectral range is now tens of gigahertz, okay, this puts a very, very, heavy, precision, okay, tight precision on the size, okay, in order to actually match, okay, two modes, okay. So if these are both fundamental whispering gallery modes, that separation is the free spectral range, and that separation scales inversely with the diameter, okay, of the device. Okay, so what was done in these two cases was a trick, okay. Basically, the curvature here and the curvature of this shape here were sufficiently soft so that in fact actually these structures would support a relatively high density of transverse modes. And so you could find, if you hunted around enough, you could find a match, okay. There was kind of a statistical chance that was high enough to find a match where this might be a fundamental mode, okay, this would be a higher order transverse mode. And you could see these Brillouin oscillators take off in lathes. All right. But as soon as you think about this, and if you have a process now like this wedge resonator, okay, where we can now define the size lithographically, okay, you realize that you can bullseye this match every time. Essentially, it's a simple calibration, okay, and I'm kind of showing that here. This is actually the free spectral range, okay. This is the CAD file target diameter, and these are measurements, okay, of the free spectral range, and our 1 sigma point is 2.4 megahertz. Okay, so what it means is that we can literally match on every single device that's fabricated, okay, this Brillouin process. And so this kind of shows you this little animation here, what we're doing. So the light blue is the free spectral range. Okay, the pump is at a particular wavelength. There's a Brillouin shift that's set by that wavelength and the speed of sound, okay, in the material, in this case glass. And so what we do is we simply calibrate the diameter. Once we know the diameter, we keep it there, okay, for all time. And then you get these very nice, okay, little, Brillouin lasers. All right. And this shows how that works in practice. Here are 4 different diameters, okay, here. And what we have done is measured the threshold for the Brillouin process. And you see that it's quite low. This is 1/10 of a milliwatt here. And we're tuning the pump wave, okay, across a whole series of modes in a given disk and measuring the turn-on, okay, the point where the Brillouin laser will actually begin to oscillate, okay, in each of these resonators. And you see that the minimum is moving and scanning across the telecom band. And so the reason for that is simply that we are scanning the FSR, and so the optimal wavelength match for the pump, okay, needs to shift, okay, so that we match, or so that the Brillouin shift is matching the FSR. So this, again, it kind of illustrates the kind of control, okay, that we have possible. All right, now, here's the exciting thing, okay. You might ask yourself, what is a Brillouin laser good for, okay? And it's just, a question I used to ask, okay, a long time ago. And because it doesn't seem very interesting. It needs a laser. It requires another laser to operate. So that's already one strike against it. Okay, it doesn't sound very exciting. You also have to do this, the special fabrication. All right. The shift in frequency is not very large. 10 gigahertz. Okay, so what? Okay, if I have a telecom laser at 1.55, I'm moving it to the red by 1 angstrom. Okay, that doesn't sound like it would be terribly useful. All right. Well, the reason they're useful, okay, has to do, okay, with coherence. All right. If we look at the line width, okay, this is kind of like a shallow town's line width. It's the fundamental line width of the Brillouin laser. Okay, that line width varies inverse quadratically with the optical Q, inverse with the power, okay, out of the device. This is a kind of scaling result that you would see in the shallow towns formula for a normal, like a gas laser, okay, for example. All right. There are some additional terms over here that are kind of interesting that not all of them you see in a gas laser. Okay, this NT you will find in the gas laser. It's not very important. This is the number of thermal optical quanta, okay, in the mode. which is negligible. It's like e to the minus 40. Okay, so it's an incredibly small number, 0. All right, there's a 1. In the Charlotte's formula, you'd find a 1/2. Right? And here you see an n sub t, this little n sub t, and this is a big difference. This is actually a noise, okay, it's a thermal noise that's contributed because the acoustical phonons are participants in the process. They're kind of in the background, okay, but they are a player, okay, in the way this amplification works. And as a result, okay, these are 10.8 gigahertz phonons. They have a lot of thermal energy. And so the interesting thing about a Brillouin laser is actually it's thermally broadened. Okay, the noise in it is thermal. Okay, for the most part, there is a quantum part. Okay, and that's this 1, and that's also interesting. Okay, that 1 comes from 2 1/2s that are being added together. There's a 1/2 that comes from the vacuum noise. Okay, of the optical mode. Okay, if you call the 0-point energy of the mode, and there's another 1/2. Okay, that comes from the 0-point energy of the phonons, and they add together and they give you this 1. Okay, instead of a 1/2. All right, so you have these little differences. This is a big number. Okay, I'll show you how big it is in just a moment. But thankfully, these are also big, and they enter quadratically. All right, and so if you measure this number, which we can do several different ways, one way is simply by using frequency discrimination with an interferometer, a Mach-Zehnder interferometer, which is what this inset panel is. Or we have another technique I'll show you in just a moment. We can measure this number, and you can actually see that it does vary inversely, okay, with power. We can also vary the Qs because we have a nice way to change the loading on the resonator with these taper couplers, and so we have data like that as well. But the main point I want to draw your attention to is down here, that the line width itself, this number is proportional to the Lorentzian line width, the full width half maximum associated with the fundamental noise, not the technical noise. I'll come to that in just a moment, but the fundamental noise. Okay, that number can be very small. Okay, it's in the range of about 1/10 of a hertz. Okay, that's a really phenomenally small number for a tiny little laser. These are little chip-based lasers. So the answer, what is a Brillouin laser good for? Okay, well, a Brillouin laser, okay, is a way of taking a relatively noisy pump. And I say noisy, it could be what we consider a very good pump. It might be a pump that has a 10 kilohertz line width, but it cleans it up. Okay, you get in the end something that has 1/10 of a hertz, okay, line width out. Okay, and it also doesn't shift the wavelength very much. And so now that small shift, that 1 angstrom shift, actually becomes an advantage. All right, you haven't really moved your wavelength around, okay, too severely. Now, just to point out that this really is the fundamental noise we're talking about here, we can actually back out by measuring all of these other parameters, this NT, okay, to fit that data. And what we find is we get 580. Okay, so again, that's the number of thermomechanical quanta. Okay, so that's just kT over h bar omega. Okay, where omega is 10.8 gigahertz. And theory would say at room temperature 569. And that difference might actually be the fact that the mode itself is hot. It's being heated, okay, by the pump. Okay, so there's just a little bit of temperature rise, okay, relative to room temperature. So this really is the fundamental noise, and it really is very, very narrow. Okay, so why is that interesting? Okay, well, it might be interesting for LiDAR. There might be some application we haven't considered yet, just in terms of having a nice high coherent source. But the one, again, I'm interested today in telling you about is actually microwave generation and using SBS. And this idea of SBS for microwave generation is not our idea. Okay, it actually goes back, okay, even earlier than this paper. There's work, okay, in the late 90s out of JPL, Lut Malecki's group. But this is a recent paper by our friends, okay, back at APL. This is Michael Dennis's group. And they've been looking at microwave generation using fiber ring lasers, okay, that are producing Brillouin modes. And this is how this works. So fiber ring lasers also will make, very, very, clean, high spectral purity, okay, Brillouin lines, because the fiber ring itself has a very high optical Q. All right, so what is done is really two different configurations to make microwaves. And this gets to this idea of microwave photonics. So in the end, we need to have two relatively stable optical fields that will be detected on a photodetector to produce a signal current. Okay, and that signal current, okay, will then be our microwave, okay, source. All right, so to produce that, okay, one way is to essentially inject two pump waves into some kind of a Brillouin oscillator, okay, such as a disk or maybe a fiber. This will produce two Brillouin gain bands, okay, shown here. You'll have oscillation under those gain bands, and the line widths are very narrow, okay. And interestingly, the technical noise, which is always there, I've kind of glossed over the technical noise, but there's room microphonics, there's thermal noise, okay, that's causing the cavity, okay, to vibrate and the temperature to change. They're all still there, okay. but they're superimposed on both of these modes. Right? So that's a common mode noise. Right? And so by achieving oscillation of these two very, fundamentally narrow lines, okay, one can detect an extremely narrow beat signal. Right? And so this is the premise or the idea, okay, behind, okay, actually using Brillouin physics to generate microwaves. Another way to do it is to use cascade. Okay, so this requires two pumps. Here's a single pump, and you can pump it high enough that this first Stokes wave will act as a pump for a second, and so you can, cascade and again, okay, detect, okay, these two stable fields. So I'm going to first tell you about, okay, just show you how this works, and it works, pretty well in DIS. And then I'm going to tell you how you can get even more out of it. All right, so here's what happens if you do this in one of these DIS. Okay, so we're our contribution here, just to be clear, is not the idea. Okay, we're just taking the idea from fibers and we're testing to see how well we can make it work on a little disk. All right, so the first illustration, I'm going to use a single pump. Okay, and we're actually going to let it cascade 3 times. Okay, cascading 3 times is easy. In fact, actually here, this is the optical spectrum measured, okay, out to cascade 9. Okay, so these things just love to cascade if you let them. So here's the pump, first Stokes, second, third, fourth, fifth. Okay, so, it's just rattling on down, producing all these lines. The sawtooth pattern you see here, okay, this is again, okay, I didn't emphasize this too much, but I'll just emphasize it again, that the phase matching process here involves actually fields that counterpropagate. So the pump comes in clockwise. The first Stokes wave is counterclockwise. Second Stokes wave will be clockwise. So it rattles back and forth. There's this flipping, okay, of direction. And in the experiment, of course, we measure in one direction. And so in this case, we're measuring in the counterpropagating direction and picking up all of these odd orders. All of the even orders, including the pump, are suppressed. All right, so it makes sense. All right. We choose 1 and 3, okay, just for this reason. Okay, so we're using 1 and 3, so we will be detecting a 22 gigahertz beat note, okay, simply because 1 and 3 are in the same direction and they're not moving in the same direction as the pump. Okay, so that's a good thing. And this is what happens, okay, when you do this detection. Okay, this is now on a microwave spectrum analyzer. This is a 21.7 gigahertz beat note, so it's a K-band, okay, beat note, and it's clean. It's a very, very clean signal. And I'll show you how it stacks up against other microwave signals that you can get commercially. Okay, I just want to mention real quickly one other thing you can do here, okay, which is to actually run this device, okay, as a VCO. There's a way to actually control, okay, that microwave signal that's generated here on this photodetector. And we do that by tuning the pump. And the reason that's interesting is that if you can tune that frequency, this becomes what you could consider an optical VCO. And there's a trick, okay, that's used all the time with normal electrical VCOs, which is to endow long-term stability on the VCO by electrically dividing it down, comparing it to quartz, and then using a phase lock loop, okay, to essentially take care of any residual, okay, low-frequency technical noise. And so you can do that with this device, and we've done it. And this shows what finally happens. So this is a phase noise spectrum. Okay, it's not worry about exactly what it means, but it's a single sideband phase noise spectral density. This is just the Fourier frequencies. But the red curve is actually what we measure for this signal. Okay, the blue dots are actually a Agilent MXG, okay, microwave synthesizer at 20 gigahertz. The black dots are a PSG. And the point of this is that you immediately get a signal, okay, that is not world or record breaking, but it's good. Okay, it's a good, decent signal. It compares well, okay, to kind of mid-range synthesizers. And you can also do another trick, okay, which is done all the time in synthesizers, which is simply to use the electrical divider to produce any signal or any frequency that would be lower than the base frequency, okay, of the VCO, in this case around 22 gigahertz. And that's what I'm showing here. This is the original signal at 22. These are replicas, or essentially divided down frequencies, okay, that have been generated with this divider. And I just want to note, okay, that when you measure the phase noise in this process of these divided down signals, okay, the phase noise improves. And this is a common feature of division. Okay, when you divide a signal down, the phase noise spectral density in signal will actually drop. Okay, and there's some kind of easy physics to explain that. If we have time, or if there's interest, I can talk about that afterwards. Okay, so now, all of this was good, okay, but now I just, in the end, okay, the net is that actually we have an oscillator that's producing signals that are comparable to a commercial oscillator. All right, and that obviously isn't good enough. I mean, it's nice, but you want to do something, okay, that's going to go beyond, okay, commercial, beyond, you know, even what might be done, okay, with electrical oscillators. This has been the vision of microwave photonics, okay, for many decades. And the vision is a good one. Okay, the physics is sound, but there's been a limit. Okay, and so I want to talk about that for a second. This is a plot that's taken from a microwave journal article. It's just showing lots of solid-state oscillators, okay, at different offset frequencies. But the point is that of this article is that you see this trend. Noise rises in the electrical oscillators, okay, as the oscillator frequency goes up. And this is a very well understood phenomenon. Electrical loss goes up as frequency increases. As losses go up, okay, noise goes up, okay, in the oscillator. All right. The vision of microwave photonics, okay, again, driven by this idea of take two laser signals, beat them together, generate a signal, vary the separation, get a new frequency. The vision of that field, okay, has been that the laser line widths themselves do not change very much as they tune. If I tune, for example, these SBS lasers across the C-band, the telecom band, the line widths do not change at all. Okay, they're just not that sensitive to the exact location in the wavelength. All right. On the other hand, okay, if we look at what's happening here, this is rising a lot. All right. So the vision of microwave photonics has been that essentially you could produce essentially a flat noise or a noise level that would be relatively independent of the frequency, and so the scaling works out really well. And that's what I'm trying to show here by this little dashed line. All right. The only flaw in the argument, okay, the weakness of the argument is that in the end, we need to detect the signal, okay, all right, and that involves a photodetector. And you can go online, okay, and you can look at the highest performance photodetectors, and the speeds begin to die out around 100 gigahertz. And so this is a great vision, but it only takes you so far, okay. It doesn't allow you to really tap into the full potential, okay, that is there of microwave photonics. And so I want to spend, okay, just a little bit of time here telling you about how you can get into this extra regime. And what we're really doing here is we're leveraging an idea in a slightly different way that was developed over 12 years ago, okay, in the early days of frequency combs. Okay, it's the basis, or it's this idea of optical frequency division. Optical frequency division is going to be it's the underpinning of optical clocks, okay, what will be the next time standard. All right, so I'm going to tell you about a different way of implementing optical frequency division that allows us to tap into some extra orders of magnitude of extra stability that are actually hidden, okay, inside these systems. So here's how it works. First of all, we're going to go over to this other configuration. Okay, right here I've got these two pumps. All right, I'm going to create, okay, two Brillouin lines. But now what I want to do is I want to actually leverage, okay, this idea that there's more stability in the system. I'm going to stretch, okay, I'm going to let the span between these two lines go out, okay, much further, okay, beyond a terahertz, okay, and ultimately many, many terahertz, but today just 1.6 terahertz. When I do that, the line widths themselves do not change. That means if we could detect the beat frequency, which we cannot, okay, but if we could, the beat frequency would have the same line width, but that beat frequency would be divided now, okay, by a frequency separation that's much wider. So this is a much more stable system. Okay, you're buying stability by simply tuning. The problem is you can't detect it. Okay, so how do you detect it? Okay, well, by using a new technique, okay, which we call electro-optical frequency division. And I want to remind you of this picture, okay, before I show it in just a moment. But this picture essentially, again, has this idea of using the SBS as the VCO, all right, and then using quartz, a lower frequency oscillator, to provide long-term stability. So we're dividing down electrically, okay, the optical produced signal to an electrical reference. Okay, what will now be done is to flip this on its head. Okay, we will still have the SBS up here. There's now two pumps, you'll see. There are two signals, these two optical signals, either the two SBS lines, but these will now be the reference. Okay, so we're putting the reference on top, okay, in frequency, and we're going to optically divide the reference down, this frequency separation, okay, to actually stabilize a microwave electrical oscillator. Okay, so the oscillator that's going to produce the oscillations we want in the end is electrical. All right, it's actually just a commercial DRO, okay, a dielectric oscillator, and so it will have enhanced stability, okay, as a result of this process, and I'll show you how much in just a moment. Okay, so here's some further details on how this works. Okay, here is the SBS, okay, system. I'm showing a couple of other possible sources that could be used up here, but these are the two SBS lines, one there, one there. Again, their alignments are very narrow. We're going to tune them very, very far apart. But how will we measure, okay, the line separation? The way it's done is we're borrowing, okay, from the subject of optical frequency division, okay, by producing a whole series of lines, a comb, if you will. It's a frequency comb. But it's a frequency comb that's produced by a combination of electro-optical modulation with lithium niobate phase modulators that are driven by the VCO that we want to stabilize. Okay, so this is the electrical oscillator. So the sidebands you see here, this separation is in fact that frequency. And also a broadener, okay, a nonlinear optical fiber, okay, that's going to give us an extra push, okay, in terms of extra phase modulation index. So in the end, what happens is this picture that you see here. Here are the two SBS lines. We have these phase modulation sidebands that are stretching in either direction, okay, one to the left, one to the right in frequency. There'll be two inner sidebands here in the middle that will meet, and we'll be able to detect those eventually. Those will be at a separation we can control. It's actually set to 10 megahertz in this case. And what you find, if you just track, okay, the noise of each of these lines, okay, if phi2 and phi1 are the original phase noise of the SBS lines, okay, you'll see that those get carried along, okay, as we produce these phase modulation sidebands. But in addition, this little phi-m is coming from the electrical oscillator that needs to be stabilized. And each time a new sideband is produced, you pick up a new factor. So you go from phi-m to phi-m. By the time you're in here, you're at n phi-m. Okay, n2, okay, sidebands times phi-m. So this difference right here produces this net phase difference when we measure that in the electrical domain. That phase difference, okay, contains the difference in the two optical signals, and it has a multiplied up or a magnified version of the VCO on it. All right. If that can be nulled out, all right, and the way that it's nulled out is we detect it and compare it, okay, with a phase-sensitive detector to a quartz oscillator, a 10 megahertz quartz oscillator. So just imagine for a moment that I set this to 0. Then you can solve this, and what you find is that phi-m, okay, if we null it out and then use it as a feedback signal, okay, back into the VCO, the electrical VCO, phi-m then becomes the difference between these two divided by n1 plus n2. All right. So you've actually you've reduced the phase noise of the electrical VCO. And this is the basic the physics here is the same, okay, as the physics that is used in an optical frequency divider or an electrical frequency divider for that matter. This is the mechanism of noise reduction. You could ask about the quartz, okay, over here. It turns out the quartz doesn't matter. It introduces a little bit of thermal noise, whether that really is 0. Okay, there is a little bit of noise over there, but it gets divided down, okay, in the end, okay, by the n1 plus n2. So this makes a great way to actually clean up the noise, okay, and tap into extra stability that was available there to begin with in this SBS system. So here's how this measurement works. Okay, so here's the red curve. These are the SBS signals beating together. The dashed is actually the VCO that we're going to clean up. This is actually the VCO in an Agilent PSG. Okay, it's a really nice high-performance oscillator. The blue is what we get, okay, when we divide by 30. Okay, there is a magnification by 30 squared, a reduction by 30 squared, okay, here, okay, in terms of the spectral density of the phase noise. And then the green is what we get, okay, when we divide by 148. And so you'll see this noise actually dropping, and it's a direct result of actually just getting access again into this extra stability. The scaling does work the way we expect it to. Okay, if we pick specific offset frequencies over here, okay, 1 kilohertz, 10 kilohertz, 100 kilohertz, and in this case we've plotted data for a whole series of different division ratios, not just the 30 and the 148. Okay, we're getting this n squared, okay, effect, okay, over here. So this really is working as a divider. Okay, right now, okay, I don't have the most recent data for this, but we've now put this at a point, okay, where at 10 kilohertz, okay, the level is now minus 143. Okay, so we've actually pulled it way down. Okay, we're down another over 20 dB, okay, even from this data. And this is simply by playing games, okay, having to do with moving the sideband, or these SBS lines out further and further. And that 143 number is now at a point where it's becoming competitive with the very, very best, okay, microwave oscillators, okay, that are available, our sapphire based oscillators. All right, I'm looking at the time right now, and I'm just going to ask a question. I think am I 5 minutes, or how far am I? 5 minutes. Okay, so All right, I've taken a little more time than I imagined. Okay, so let me just kind of say a few things, a few highlights here on the last couple charts. And another subject of great interest right now is frequency microcombs. This is another process or another kind of device that leverages another nonlinearity, the parametric nonlinearity. I'm just going to mention very quickly that frequency microcombs are now implemented in many different platforms. Okay, the toroids, silicon nitride, okay, the mag fluoride, calcium fluoride, okay, little micro machine structures here. And so this is an application that's driven by the idea that frequency comb technology, okay, I know there are many practitioners and users of frequency combs here, has become so important, okay, for timekeeping, spectroscopy, that the idea of transitioning it from a tabletop, okay, or benchtop style system onto a chip is an extremely compelling idea. Okay, and so the physics, okay, again, this high Q nonlinear physics, in this case, combination of a parametric oscillator, okay, with four-wave mixing, okay, makes frequency comb technology possible. We're doing these, making these little devices with these disc devices. This kind of shows you how a comb grows. Okay, it starts, okay, with a pump wave, a signal and idler, and then these extra two little peaks you see here. And then it grows and grows. Okay, if you pump a little harder, you'll see more lines. And then eventually, okay, you pump a little bit harder, and the whole spectrum fills. And so this is one subject I just want to touch on and mention here. Okay, and then one last subject, okay, that ties in with frequency combs, and again also with microwave generation, is the idea that optical frequency division, okay, what I've described, okay, in this case of these SPS lasers, was invented first in the context of frequency combs. And so one of the key ideas, or one of the key drivers for interest in frequency combs, microcombs on a chip now, is the idea that that kind of technology, in terms of making very stable microwaves, could itself be put on a chip. And I just want to leave you, okay, I'm going to skip through these charts and apologize for not leaving time to talk about them. But I just want to mention this. Okay, this is something I find very inspiring and motivating. This is again not our work. Okay, this was actually work out of Scott Didham's group at NIST in Boulder, Colorado. And here's the paper. Okay, the first author. But this is a block diagram, kind of my own little block diagram of actually how you generate stable microwaves using a frequency comb. So again, a different style of microwave generation that preceded what I discussed earlier, this based on this electro-optical frequency division technique. But here's the idea, okay, that, and this was all demonstrated in this paper. If you take a laser, it has to be a fairly stable laser to begin with. If it can be cleaned up, okay, somewhat by locking it to a reference cavity, then this laser source itself, okay, when run into a frequency comb, okay, and locked, okay, or used to stabilize one tooth of the comb, okay, will actually produce, if we measure the output pulses, okay, from the comb, a very, very stable microwave. And the process here, okay, you'll see this division sign is the one I referred to earlier called optical frequency division. Okay, one of the miraculous tricks, okay, that's performed by an actual frequency comb, a self-reference comb, is that it can take optical signals, okay, running at hundreds of terahertz, and it can divide them down coherently, okay, to a detectable rep rate, okay, that can be processed electrically. And that rep rate, okay, is given by the pulses coming out of the mode lock laser, okay, which forms the core, okay, of the frequency comb. So if you think about this a moment, and you think about the chart I had up earlier, okay, of the effect of frequency division on phase noise, all right, when we divide a signal down, phase noise drops quadratically with the division. Okay, the division factor here is from optical frequencies, okay, hundreds of terahertz, okay, down to a microwave signal at 10 gigahertz. So the division factor is in the range, it's above 50,000. All right, so when you square 50,000, okay, you're now above 10 to the 9. All right, so there's over a billion, okay, reduction, okay, in the phase noise in coming from whatever you can achieve here optically, okay, into the microwave domain. All right, and so as a result of that, the very, very best microwave signals, and again, this is what I find very inspirational, are now generated by frequency combs. Okay, And meaning that even the state-of-the-art electrical microwave sources again based on these sapphire devices are now exceeded in performance by this frequency comb technology. Now you can even go further, of course. If I tied this to an atomic transition, I would get a stupendously stable signal. This is the basis for optical clocks. But the interesting thing here is that reference cavity technology, just Fabry-Perot technology, is already good enough, that you can do this, without having to get into or enter into the atomic physics. And just to show you, again, so a completely different application for microcavities, and then I'll conclude. This is what, the state-of-the-art sort of reference cavity now looks like. This is out of Jun Yi's group at Jilla. The cavity has a relative Allen deviation of 1 times 10 to the minus 16, which is a phenomenal number. I think it's going to be extremely difficult, for microcavities ever to approach that number. But that's the cavity that is essentially used to stabilize a laser. The laser is then divided down to microwave rates to produce these incredibly stable microwaves. So it is this cavity essentially that's setting the reference. In the end, it's an optical cavity. And so all of us now that are in this frequency comb business, again, this is not a complete list of all the platforms, but you can see a number of them there. All of us that are in this frequency comb business are now thinking, can we make a reference cavity? Is there a good way to make a reference cavity using our own particular technology so that it could be tied together in some kind of a miniaturized and maybe even chip, integrable, format? And I'm going to skip through the last couple of charts here, which I was going to tell you about some of our own efforts on frequency referencing. And I'll just have to refer you to our website, on that. But to conclude, I want to thank the colleagues at Caltech. Also, we've had a collaboration with the Diddams group at NIST for a number of years, and I wanted to acknowledge Scott Diddams and Scott Papp there, and also our funding from DARPA. And this is kind of a summary of this sort of quick journey that I've tried to take you on today, beginning with toroids, to DIS, and I didn't have time to talk about these, but this is the reference cavity technology based on these so-called spiral cavities, and then some of the applications, microwave generation, frequency combs, and then again the reference cavities. And I'll just conclude again by saying that thank you again for the invitation to be here today, and like I said, I always love a chance to share my own enthusiasm for this field, and I hope you can find time to work in it yourselves. So thank you very much.